I am trying to figure out though if it's something that I inadvertently, because this thing is sensitive, is there a shortcut that I'm pressing? But I don't think so. And another thing that I'm doing, I'm duplicating. Maybe I just need to, because I'm recording my view, and when I record my view, this is it. So I click duplicate slideshow, and I think maybe that part, that's when the tulips show up. There's going to be a test if I'm going to reproduce that. Yep. No. So now I duplicated correctly. But I think that's the step where possibly those tulips show up, and I have anyway, learning the ropes. All right. So the whole point is that we might have very different images in our hands, and some of this introduction will kind of look at some of the different images that we have, and then we're going to look at what are images themselves. So if I look at this, this is a thin section. Everybody knows what thin sections are. We inject epoxy into a porous medium. Epoxy shows up as blue. Okay. And then I do, this is light microscopy. And I can expose it to different types of light, polarized light, whatnot. And this is the most common, so you have to have a thin section of a rock. And this is the one of the most that is specially prepared for this type of imaging. And this is the most common one, like that is done at scale. There's a lot of thin sections. Geologists look at the thin sections, and what they typically do, they do point counting. So they throw a raster of images. A couple of hundred is typically taken as a standard, and then based on where they fall, they quantify what the porosity is, or whatever other phases they might see. Okay? So that is a common way to quantify porosity, and that's often what's on as part of the porosity log in well logging. Okay? So one would like to automate that, right? Now we also want more than that. We would like the same process be done in 3D, which is where different types of imaging comes into play. So there's an array of imaging modalities that we will go over. And I'd like to analyze things in 3D. So this is a cross-section of a three-dimensional image. And I would like to quantify everything and anything in there, from porosity to volumes, surface areas. And I would also like to possibly then go further and get permeability, formation factor, all kinds of elastic properties. Now, I have to adjust my imaging to the scale. There's a whole lot of imaging that is done with seismic imaging. I do not know much about those images, right? But in essence, they are still images, and I'm looking for features in those images that have to be interpreted. But seismic is such a large scale that you have that's a complete different set of skills than what I, for instance, have, even though I've looked at a lot of images. So one has to, images are images in the sense that they're arrays of numbers that correlate to properties in whatever it is that was imaged. But that said, interpreting them is non-trivial. If you have a type of rock, you have to also decide what is the scale that you're going to image on. So in this basalt rock, you could try to focus on these openings that are millimeter scale, or you could try to focus on the matrix, for which you need different types of modalities. So this you would image in a regular medical CT, and the details of the matrix, you would have to go to microtomography. And those are two different price points too, right? so you have to know where to go and what to image. And we're looking for certain features, and based on the features that you're looking for, you're going to decide what type of image you're going to take. Now, you would like some measurements that validate whatever modeling effort you have at hand. Okay, so here's one example that was done here as part of the PhD thesis. So basically, and this is how the imaging itself was prompted. Okay, why would I and when do I need to go image? If things go as expected, you don't necessarily need to image, so don't, right? If things go unexpected, that's when you need to image. So here there's these are tracer floods. So everybody knows tracer is injected. I expect tracer to show up on the other end after I inject what's equivalent to 1 pore volume of the rock that I had. Okay. So that's when I would, like, if my rock is relatively homogeneous, that's when I expect the front to pass through, right? And I'm going to start seeing most of the stuff after 1 pore volume, right? Now, that's also correlates with certain time that is correlating with the permeability. So if I have this is sort of a regular tracer test through a relatively homogeneous core. I have, even though my wave initially started as just like for a certain amount of time, I was injecting, right? The stuff that had tracers, so that was initially like a pulse, like a block pulse. But of course, because of the rock heterogeneity and tortuosity through the rock, I will get this smoothed profile come on the other side. But overall, most of it kind of shows up at the same time and passes through the rock, right? So this is the classical example. Now, there was a second core that looked from the outside very similar to the first one. However, I had what's called early breakthrough. Some of these tracer showed up way too soon, way before 1 pore volume was imaged. So something was in there, and that something had to be found out what it is. Okay, this is where I'd like to image within to see the core. Now, this is basically how this is one cross section through this core. This is a carbonate sample actually here from Canyon Creek, close to Austin. And when you look at the X-ray image, there are some of the vugs in there, but those vugs didn't appear connected on a large scale, but maybe they are. Maybe that's the reason for a breakthrough. Okay? And one thing that actually, here's a movie, we'll start. Let's see that this movie doesn't stop my video. It doesn't. Okay. So basically, there is this movie through the entire core. You can see the vugs. There's some further calcified features. These are former shells within a carbonate core. And maybe I need to figure out how to speed up this movie. And this is where you can actually see start of a fracture through this. And it continues for the rest of the core. This was image of a core that was basically used in the lab. And this fracture becomes bigger. Okay. And this is end effects in imaging that are on top and bottom of the image. So basically, so there's this dominant phase is actually this lighter gray, but there is a fracture through, and it seems that on the top part of the image, for sure, it's connecting these vugs, but it seems that it's enough to actually allow for this relatively fast going through the image. And I say relatively because it's faint here. However, any opening that is actually a clear opening through this core is way bigger than this majority of this microporous phase that I have in the image. Just the fact that I see it as a fracture means that it's probably 100 times bigger in terms of cross sections. So it doesn't look much, but it is much compared relative to the rest of the matrix that we have in this. And this was imaged with relatively poor microcity resolution, but it was focused, the core actually, I have it somewhere in my lab. It's this big. I found it during the lab cleanup, and I recognized these cores that were in this 2008 PGE piece, so I actually kept them since I have their images. I figured that it's nice to have them. I'll try to bring them next time. So basically, there's this fracture or crack is more or less connected throughout the samples of this core. So this is qualitative. I imaged and I looked at it, and this might be already enough for you to just say, okay, I know what's happening in this core. Right? It's not a surprise to me anymore. There's a fracture in there. Ideally, though, one would possibly want to quantify this fracture and find it. In itself, anything thin is hard to find and correctly identify in an image, and we're going to get to that. So the comment is that the ability to quantify depends on the image. That one was certainly not an ideal one to quantify anything on. So one would actually have to spend some time to actually get both to quantify porosity and to get the connectivity of the fracture and the bugs. So if you have more details, this is a sandstone example, then you can actually do better. But then you might not be imaging the entire core that you, for instance, used in your experiment. So those are the trade-offs. Field of view kind of remains the same. So that is the, again, objective of the image analysis of any such image is to segment and identify and then find the certain objects in your image. And that could be vugs, fractures, individual minerals, and so forth. And then based on that, figure out how they connect and how that affects the transport in your core. Okay? And then you would like to fit things into a model so you can use them for later. So that's the workflow that I already explained. And this is just before we move on to actual exercise. What is this image of? Just for kicks. It's a porous medium. It's not a rock. Sponge? Close. Keep going. It's spongy. Apple is porous. So I found this because they were actually citing my work at some point, and I was like, what is this again? But they were actually looking at the porosity of two different types of apples. These are, by the way, the types of apples. Sometimes you can buy Bradburn around here in Yonagold, but they're not super common. But anyway, they were relating, I guess, taste of apples to their features. I've also seen people studying bread in X-ray machine. It grows fast and porosity changes really quickly on an X-ray. It's easy to image. It's not like rocks are dense, so they're take a moment to actually collect enough statistics on the image. With bread or apple, it's actually a faster process. Anyway, there's a lot of porous media out there. All right. I don't see why not. I mean, as long as you stopped imaging, the apple itself is not going to radiate. I don't think it does. Right? Just like you don't, like if you go for CT imaging. Yeah, yeah. I don't think it's a lot of radiation after the imaging itself is stopped. As long as you're not there during the process. That's why you have to have the precautions when imaging, right? So I don't think just by consuming something that was imaged, I don't think that's, or certainly it would take a long while to accumulate. The problem with radiation is that your body remembers for every CT image that you've ever taken in life, it accumulates. But that said, I don't think eating something that was imaged. But don't eat rocks, okay? They absorb more than an apple, that's for sure. So, anyway. All right, they're denser, therefore they retain more. So when I look at one of the images that I've shown you, okay, we have to understand that all they are really is a matrix of numbers. So actually this, if you zoom into this, so here you kind of see two phases when you zoom in. Would you actually be able to draw a clear line between a light phase and a dark phase here? This is where uncertainty starts. Okay, so when you need to tell software, hey, put a line here in between these two phases, there's a bit of a smudge happening. And that smudge, we're going to go into details why it happens, but it's going to be there. It's called point spread. Okay? When I look at the numbers, literally, this is a number, this is a number, this is just a visual representation. But you look at the image, including the screen, is a visual representation of numbers. If it has color, that it's 3 superimposed images, really, or 3 superimposed matrices of numbers. So this is 220, 215, 210, and so forth, right? So those are numbers. So I have to figure out how I'm gonna store these numbers for one. Okay? And the simplest way when I have one of them is to store it as an array. However, the moment it's a 2-dimensional array, I have choices of how to pack that array into memory. Have you ever worked with that in simulation or otherwise? Same happens in numerical representation of a 2-dimensional domain. It's an image, essentially. It's a bunch of numerical cells. So basically, I have a choice of going this way. So I'm packing in contiguous memory. Okay? I can go row by row, or I can go column by column. Which one is right? Either. And the software you have uses either. You often don't know. The only time you find out is when it bites you. If somebody is giving you a binary array without any other preamble telling you what's happening, and you go from, for instance, C to Fortran, or anything that does things like C and anything that does things like Fortran, there is a dominant programming languages that we're using right now. In those, there are 2 groups. So if you go back and forth and you don't know that, issues can be had, and we're going to have that. So that's it. So we have to pack them. We also have to decide how much space is each of these numbers going to take. Okay? And if I have numbers that are limited in value, so there are 0 to 255 is one range, one common range, 1 byte is enough. If I have only zeros and ones, 1 byte is enough. And zeros and ones, I can also pack very efficiently into smaller memory if I wanted to. Okay? They kind of zip very well. So I need to figure out how do I represent the images. We're not going to go into vectorized images at all. They're not very common for storage of imaged values. We just have to know what is the type of, often we have to know, what are the type of numbers that are used to store the values that I have in the image. Okay? Are they integers? Are they floating points? Floating points is real numbers. And if there are real numbers, and in either case, how much bytes is used per image? 1 byte, 2 bytes, 3 bytes. Okay? So again, this is just 3 different visual representations of the zeros and ones. Okay? All of them are just that. They're visual representations. Most of the time, what we see on screen is something like this or something like this. But when you kind of zoom in, you can see a rasterized image, just like when you walk into any kind of screen or projector. Okay? So this is just visual representation of the velocity, or rather speed, through a 2-dimensional image. This is a result of a simulation through that little polyethylene core. So we see the fastest flow here, the slowest flow here. Okay. So storage, we are often stacking things. Now, if you come in some standard image type that your phone would read, like TIFF, JPEG, PNG, bitmap, those have standards, and most of the software knows how to read them. That's good, because then all of the underlying problems, do you have 1 byte, 2 byte, 3 byte used for per point, is not important, or not that important. It's really important just like in the memory you use. Okay? But that said, most of the software will know how to read it. However, often it's just raw data, just numerical values. If you go through any numerical course down the line where you're asked to do simulation, again, results of the simulation, depending on how you program it, are typically just some sort of raw data that you kind of read in or spit out during your simulation. Those are images as well. They're essentially images. Right? So all of these values are somehow packed into two-dimensional and then three-dimensional space, and you need to know how that is done. This packing is often done by packing as following. So index in your file, I'm packing things into one dimension. Okay? That packing is, for instance, number of slices k times nxy number of values in one slice, plus j, that is the value in so ijk point, j times nx is the length of a column, plus I. And if I flip what it is that I'm representing in terms of rows and columns, I can flip I and j here. So I could go with I times ny plus j, with nx is nx, ny, nz, right? Number of points in each direction. Is everybody following what I'm talking about?
Why isn't it just like
because it has to be unique. So this way, I'm actually making sure that essentially, if I'm thinking about this in a line, I'm packing here all of these columns first inside the first slice, first one after another. Okay? And then I go to the next slice. And then I go to this way it's uniquely defined. So everybody in the first initial slice is there first, then second slice, then third. So I'm talking about one-dimensional array that is continuously in memory. So to go to a three-dimensional ijk location, you go back and forth. But this means that so when I put k is equal to 0, all I have is this j times nx plus I. So that's my first slice. And once it's done, I have nxy values. And then the second slice starts, so k is equal to 1. And then all of that. So I have to skip these first nxy values in order to get to the second slice. Right? And that's, right? So basically, in order to get something, so if you just think about storing this entire thing into array, you have to, let's say that you're going down the first line. The second line, or second row, is going to go after it, then third, then fourth. To get to the second row, you got to skip the entire first row. And that's essentially what this is doing. When you set it to larger values. When it's 0, you're still in the first row. So in memory, you got to do that. If you're stacking multiple dimensions, and if you had more dimensions, you would keep going. And the computer can easily figure that out. For us, it's hard to visualize. Yeah. So you need to know range, and there's certain terminology that goes with knowing what these are. 8-bit image is 1 byte. Word in a computer is 1 byte. 1 byte has 8 bits per 1 pixel or voxel value. So whatever it is that I want to store, I'm using 8 bits of memory to do it. Okay? And these are often also referred to as unsigned binary characters. 16-bit is 2 bytes per pixel or voxel. And it could be unsigned or signed. If I talk about storing a signed integer into memory or not, is everybody familiar what This is a little bit of computer science, sometimes is baked into introduction to numerical analysis. So very short, if I have 8 bits or 16 bits, it doesn't matter, and I'm using that memory to store integers. Okay? The way I store, there are rules that are baked into how am I going to organize those bits, pretty much. For a rule for integer is different than the rule for floating point. Okay? Because in floating point, you can imagine you have scientific notation, so it's something times 10 to the something else, right? So you got to store both that exponent and the actual number. In an integer, you're just storing that integer. So there are two different rules. We're just going to leave it at that. In integers, I could decide to reserve one of those bits for sign. So if it's 0, it's positive, otherwise it's negative, or not. So if my range is 0 to 55, great. That's unsigned integer, and I can store that many numbers in 8 bits. Or I can decide to store numbers or interpret them as storing numbers from minus 128 to 127. It's all a matter of agreement, and rules exist for storing and organizing these bits and bytes one way or the other. But you gotta know what's stored. When you look at the 1 byte of memory, you gotta know how much it's stored. And you're looking at the memory, okay? You also have to know, well, are the numbers that are coming in, let's say there's just 5 numbers. It's one dimension, 5 numbers. Like we're not even packing any arrays or anything, right? I gotta know whether to read for those 5 numbers 5 bytes or 10 bytes. If I don't know when to start and stop, I might reach into the memory that is right after this that is storing something else. That's corruption. That's when like your file is corrupted. You reached into the memory you weren't supposed to reach into, right? So you didn't know how much to grab and you grabbed too much. In the process, you could also damage the memory that way or like overwrite something. Or you inadvertently went in your class for numerical analysis or something, you're reading and writing, and you open up and you overwrite. You open the memory for reading and you start writing, and you overwrite something that was there before. That's memory corruption too, if you made a mistake in the process, right? So that all happens in this, and it's important because it can cause quite a headache if you don't know what type of images you have and you're reading them or writing them wrong, and you don't know how somebody organized them. So again, I have to know whether it's an integer. I have to know how many bytes. I have to know if it's an integer, whether it's signed or unsigned. Floating points always have a sign, no problems there. But it could be 32-bit or 64-bit. The 64-bit is so much memory that it's rarely used. And then if I have colored images, I have immediately decided to use 3 times more memory than necessary, often. Especially because in imaging that we are interested in, the color is fake. Color is there for beauty. Color is just the interpretation of a single numerical range. Okay? So if Javier is imaging a lot in his micro CT, the information we get from micro CT, interpretation of that micro CT, is one number. It's X-ray attenuation. There are no 3 numbers. You get one number. Choosing colored image for that one number is waste of 3 times as much memory as you need. Plain and simple. Because those other colors are not capturing anything important. They might be pretty on the screen, but that's it, right? It's more memory. And then final fun. Has anybody ever heard of Big and Little Endian? I can, just like in reading, read from left to right or from right to left. Actually, I can also read, is Japanese going top down or down to top? Anybody reading Japanese or anime? Or no? Anyway, it's a matter of agreement. There's no right or wrong, right? There's like an agreement whether you go from left to right when you read something. Is your beginning on the left or on the right? Who's to say? Okay. Well, when I have 2 bytes that I'm storing in my integer, I can read them from the left or from the right. And computer could care less, just tell them what to do, right? Now, if you are writing something into memory, okay, you're writing it on a machine that uses, it's called Little Endian, and you give it to Bernie, and Bernie is using a big Endian machine, you just scramble. You're gonna read it from the wrong side, and you're gonna read a bunch of garbage. You just scramble that information. So that's an important byte order. It's called byte order. So this Endianness is little endian versus big endian. And you have to know the larger the files, more likely they're sensitive to this because they're not going to use the most advanced formats because most advanced formats cost memory. Okay? All right. So there's a way to tell, though. You can actually go online on a web page and ask, what is my endian? And you will, you will actually be able to find out. So we can actually test that right now. So there is even browsers, web browsers have to be aware. My endian. Let's see if that really works. Oh, come on. Typically, there's definitions now. Tell me my endian. Now it's going to tell, okay, I know how to program it. That's what I was trying to avoid. I'm sure there is a web page to tell you what your endian is. This would be a way to tell in a code. So basically you can actually test, you can read a piece of memory and see which side actually makes sense. And this would be a C code to test. In MATLAB, you can go and read any file, just open whatever file you have on your computer. And then there is one part of the description of that file is machine format, and it's L for little endian and B for big endian. So there are tricks to find out on your own machine which one you have. Okay. I think we're just now exercises. I'm just going to give you one to think about. This is not opening any software. But let's say that a colleague informs you that they will send you a DVD with data. DVD is an outdated form, but they will send you some link where you can download data. Their brand new scanner, and it has 20, let's say that it has 2,000 slices, and each slice of the image has 2,000 by 2,000 pixels. So each slice stores 16-bit TIFF images. So you're using 16 bits for every number, 2 bytes. And you're planning to analyze this data on your laptop, and you have a little older laptop with 8 gigabyte of working memory. Can you actually read this entire image into 8 gigabyte of memory? Nope, you need 16 just to read it. 2,000 roughly by 2,000 by 2,000, that's 8 giga is 10 to the 9 bytes. You're storing 8 times 10 to the 9 numbers, and for each you're using 2 bytes. That's 16 times 10 to the 9. So you can't even read it. You read half of it typically. And you can work with a half, but you can just, with your working memory, just look at it. Right? You can't do anything with it. Right? So these are certain, and this is a common type of image, right? So something to think about. All right. Well, we're going to get to our exercise actually in ImageJ next time. So, oh well. So bring your laptops.